Very good afternoon, everyone. Today we are going to discuss in the second lecture, that is velocity and pressure distribution. In the previous lecture, we discussed about the basics of open channel flows. Then what are the different differences between a pipe flow and open channel flow. Then we discussed further about the types of channels and the types of flows. Then we classified the flow conditions based on that. And now we'll move further and discuss the velocity and pressure distribution in case of open channel. So, as you know that in nature we usually encounter non-prismatic channels. So that channels can have irregular boundaries. Even the surface of can be irregular, will not have a uniform surface. Some stretches may be vegetated, some stretches may be without any vegetation, or maybe having rocky particles, and that could be the possible case. Also, the alignment is not fixed. The river may not be straight for its longer reach. It can have bends and all. So these all factors affect the velocity distribution. So you can see that there are two channel sections being presented. On the left there is a non-prismatic, on the right you have a prismatic channel section. So you can see some sort of contours being plotted here. So what are these contours? So there are some values being given, 0.8, 0.76, and also these contour values have been given. So they are the contours of equal velocity. So if you have different points, if you measure the velocity in an open channel, and that points are joined and they form these contours, and they are called isovels. So an imaginary line which joins points of equal velocity are called isovel. So similarly, in case of a prismatic channel also you can see the isovel. But you can see something, that the shape of the isovel is some way or other governed by the cross section. So here you can see that the channel cross section is bit wider, so the contours are having a more wider perspective, and here the contours are having a very narrower perspective. So that depends. So usually in case of an open channel flow, due to the presence of free surface and due to friction along the channel wall, the velocities will not be uniformly distributed. So you have this wall friction one, and then again the free surface. So at the free surface you have two different fluids interacting. Here it is air, here it is water. So due to all these factors, there is some sort of resistance being offered, due to which the velocity distribution is not uniform. Next, also as we discussed, the influence of channel geometry is also apparent. So I mentioned a wide channel and a narrow channel, so that is also there. So the velocity is zero at the solid boundary. So wherever you are taking at the boundary, your velocity is zero. Okay, and it will increase gradually with distance from the boundary. So as you move away from the boundary, your velocity will increase. But at this point, where you have the contact with the boundary, your velocity will be zero. Now, this is at the cross section. So if I take, let us say, a particular cross section to see, let us say if I take this cross section and see what is the velocity distribution. So that can be visible here. So looking at this, we can see that at the channel bottom, that is the velocity is zero. At this point your velocity is zero, and as you move away from the boundary or channel bottom or the side boundaries as well, your velocity will gradually increase. So this will follow either a logarithmic distribution or a power law distribution. So your velocity will gradually increase as you move away. Now ideally the maximum velocity would be at the surface. So this is the surface. So ideally the maximum velocity would be at the surface, but actually it is not at the surface, because uh, due to some factors, which first factor I mentioned, that there is a interaction between two different fluids, that is you have a liquid water interface, so that also offers some resistance, so that is density change. Now the ideally if we follow this distribution, it should have a maximum velocity, but actual it is not. So this difference between the maximum and actual velocity is called velocity dip. So the dip of a maximum velocity point would yield the surface velocity is little less than the maximum velocity. That is first due to the secondary currents which are being generated due to the density differences, and second, it is also the function of the aspect ratio of the channel. Now what is aspect ratio? Aspect ratio is the ratio of width depth to width. So based on that, we classify the channel into wide channel and a shallow channel. So if this ratio is y by b, that is greater than 5, then we call it as a wide channel, and if it is y by b is less than 5, we call it is a narrow channel. So that is the ratio which is there. So interestingly, if the maximum velocity is not at the surface, then where is the maximum velocity? So maximum velocity is at this point, that is zero point 0.2 times the depth. Now y0 is the entire depth, so it is 0.2 times the depth below the free surface. So at this point you get the maximum velocity. Now the average velocity is obtained at a distance zero point 0.6 times the depth from the free surface. So that point you get the average velocity. So the average velocity is computed as v average, that is the average of v at point 2. So this point 2 means point 0.2 y naught distance from the free surface, and v at point 8 means 0.8 y naught distance from the free surface. So that will give you the average velocity. Now usually the points of maximum velocity would depend on many factors. So if your channel is, let us say, is wider or channel is deeper, that factors can affect, and that is what our point of discussion is. So is it that the point of maximum velocity would depend on the aspect ratio, or it will be independent of the aspect ratio? So in aspect ratio, let us say if you keep the depth as constant and you change the width, then you can have a fair comparison, that is one parameter is constant. So that is a point to ponder upon, that would they change or would they be similar. Now uh, where this is important, that the velocity computation will help you in estimating the discharge. So usually in field, how velocity is computed, so let us say this is a cross section of a river and this is the flow depth. So there are some devices, so most widely used is a current meter. So what they do, they divide the entire cross section into different strips. So I'm dividing it to some strips. This is strip V1, 2, 3 and 4. Now using the current meter, I know where I can get the average velocity. So average velocity is available at 0.6 from the top. So I'll insert my current meter at the center of the strip at a distance 0.6 from the top, and I'll get V1. Similarly, I'll get here V2. I'll come at this point, I'll get V3, and I'll get here V4. So I multiply the velocity with the area, and then I'll get the discharge, or you can get V1 Y1, and then you can multiply by the width also. Okay, so similar that way you get the total Q as summation of Qi Yi Bi. So that this is your total discharge which is passing through each cross section, then it is summed up. Okay, so that will give you your total discharge passing through a section, and that is why it is very important that at which point you measure the average velocity. Now let us say if you don't have the average velocity, you have the surface velocity. So there is again a relationship between the average and surface velocity. So if you got a surface velocity, that is Vs, then the average velocity is 0.8 to 0.95 times the surface velocity. So usually surface velocity is measured using floats. So there is a float method, and you compute the velocity with the help of distance traveled upon time. So that will give you the velocity, and you multiply by coefficient. Now this coefficient depends upon various factors, that is the field conditions, and also they are derived from field calibration. And if you know the surface velocity, you can also find the average velocity. So this method is independent of the current meter. Using the float only you can do that. Okay, so moving further, now we discuss three kinds of flow, that is 1D flow, 2D flow, 3D flow. Now since a 3D flow analysis can be very complex, so in for most engineering problems we resort to 1D flow. Okay, 3D flow can be done, but it becomes, you know, very complex, that you analyze all the three dimensions. So the flow properties, such as velocity, pressure gradient in open channel, can have components in the longitudinal as well as the normal directions. Now that can be very complex if you consider all the three components. So we will go by the simplicity and we'll take only a one dimensional flow. So regarding velocity, a mean velocity v for the entire cross section is defined on the basis of the longitudinal component of velocity. So we define v is equal to 1 by a integral, that is area integral v into dA. So that way we define it. So where your capital V, that is the mean velocity for that cross section, and small v can be the velocity at that particular, like we have four strips, so in that particular strip, that is the small v, and that can be, you know, integrated over the entire area, and you can find the mean velocity. So similarly discharge will be integral v dA. So that is v into a, so that will be the total discharge that will be there. Now uh, due to the non-uniformity in the velocity distribution, as well as the pressure distribution will also be non-uniform, because velocity and pressure are interrelated. So the equation is not as simple as we say that v q is equal to simply va. There has to be some factor which has to be responsible for this non-uniformity. So, due to the non-uniform velocity distribution, the velocity head of open channel flow is greater than the value computed using the expression v square by 2g. So, where v is the mean velocity and v square by 2g is your velocity head. Now, what happens? The than the computed expression, the actual one is greater. So, you need to apply some correction. So when the energy principle is used in the computation, the true velocity head may be expressed as alpha v square by 2g, where alpha is your energy coefficient or Coriolis coefficient. Now this correction factor that has to be applied, if there is no information given, you can take it as unity, that is 1, otherwise you have to apply it. Now uh, since the velocity, if you go by the definition, okay, force is equal to mass into acceleration, and the force component, if it alters, then it will also affect the momentum in an open channel. So the non-uniformity in the velocity will also affect the momentum in the open channel, and similarly the correction factor that has to be incorporated to represent the momentum of fluid passing through a channel per unit time. So that is beta. So it is beta W. This is the unit weight of water, QV divided by G. So your beta is your momentum coefficient or Boussinesq coefficient. Okay, so now we'll derive the values of alpha and beta, how they are computed. So for that, what we will do, we'll take a elementary area in the whole water area. So if you have the entire water area, you take a smaller area, that is delta A, and your W is the unit weight of the area. So what is the weight of water which is passing the elementary area delta A in unit time and given velocity V? Okay, so that is nothing but W into V into delta A. So this is the weight of water. Now what is the kinetic energy? You multiply this weight into kinetic, that is velocity head, V square by 2g. So that becomes W V cube delta A by 2g. So if you want to have the total kinetic energy, what you will do? You will make a summation of this kinetic energy at each section. So that is the total kinetic energy for the whole area is sigma W V cube delta A by 2g. And if you want to compute the kinetic energy flux for the total area, and that we can equate to the velocity head for the whole area. So this is a kinetic energy flux, and that we are equating with this velocity head for the whole area, that is integral A W by 2g V cube dA, that is equal to alpha W by 2g. This is capital V, that is the mean velocity, V cube A. So rearranging this equation and solving for alpha, so we get alpha is equal to integral small v cube dA upon capital V cube A, or it can also be expressed as a discrete form. So this integral is a continuous form and this sigma is a discrete form. This sigma V cube delta A upon V cube A. So this alpha is dependent on the third power of velocity. That is the kinetic energy correction factor. So if you have the velocity distribution available, based on that you can easily find the correction factor alpha. Now similarly, we can also derive the momentum correction factor. So the momentum of I mean the momentum of water which passes through delta A per unit time, that is given as momentum is mass into velocity. So since the velocity is non-uniform, your momentum is also non-uniform. So that is your mass is W V delta A by G as discussed previously into V. So that is velocity. So it becomes W V square delta A by G. So it is dependent on the second power of velocity. So total momentum, again you sum it up for each cross section, that is W V square delta A by G, and the momentum flux, that is integral of W V square dA by G, that is equated to the corrected momentum for the whole area, that is beta WAV square by G. So rearranging and solving for beta, we will get beta is equal to integral V square dA upon capital V square A, that is sigma V square delta A upon V square A. So here your beta is dependent on the second power of velocity. So you can compute the kinetic energy and momentum correction factors based on the velocity distribution. Now if your velocity distribution is uniform, what do we mean by uniform? Let us say it is something like this. This will be uniform. There is no change throughout, so that is a uniform velocity distribution. Okay, so if I sketch it, it will be something. So this is a uniform, there is no variation. So for that case, both your alpha and beta will be unity. For other velocity distribution, your alpha will be greater than beta and that would be greater than 1. Since alpha is proportional to the third cube, so always it will be greater than beta. So the higher the non-uniformity of distribution, greater will the values of this coefficient. So it all depends on this velocity distribution. If this distribution is non-uniform, the more the non-uniformity, this coefficients will be higher. Okay, if there is no specific information, we can assume the coefficients to be 1. However, there are certain cases where you have been given the values of the coefficient. Let us say if there is a natural channel, then the average velocity of alpha can be considered as 1.3 and beta can be considered as 1.1. If there is a river valley, then it is 1.75 and this is 1.25. So you can see the values of alpha and beta are also not constant. So that prompts us to our next discussion question, that does the channel aspect, that is the dimensions of the channel and its alignment, affect the values of coefficient alpha and beta. So what does alignment mean? Let us say this is a straight alignment and there could be some like curved alignment, or there could be a severe bend alignment. So would this, apart from the aspect, you have already known what is an aspect, this is these are the aspect, so would these factors also affect the coefficient? So just think in that way, that whether these two factors affect the velocity distribution or not. If they affect the velocity distribution, then they can affect, but in what way, that is the linkage you have to establish. That for, let us say, narrow channel or wider channel, straight alignment or curved alignment, where there will be more non-uniformity and where you can expect larger variations of alpha and beta, that is a point you have to think upon. Okay, now moving ahead, we will discuss the pressure distribution in an open channel. So in case of pipe flow, if you wanted to measure the pressure, then we use to have a piezometer, so that would give you the pressure in the pipe. Okay, now in case of an open channel, what happens, that there is a free surface, so the pressure at the free surface would be equal to your pressure of the surrounding atmosphere. Now usually the atmospheric pressure is taken as a reference, so that value is taken as 0, because with respect to that we measure the other pressures. So the pressure at your free surface in an open channel, that is considered to be 0. And usually the distribution of pressure in an open channel, that is driven by the acceleration due to gravity, because gravity is a predominant force in case of open channels. Now the since we need to measure the pressure in a open channel of very small slope, then the height of water column in the piezometer will be noted. Now usually the minor disturbances that occur due to some turbulence and all that are neglected, and the water column, whatever the pressure or the value is being shown in the water column, that we considered as the pressure at that particular point. Okay, now therefore the pressure at any point on a section is directly proportional to the depth of point below the free surface, and that is equal to the hydrostatic pressure. So as we discussed, free surface, your pressure is 0. So whatever the depth of water column that is below the free surface, that is directly proportional to the pressure, and this particular phenomena is called the hydrostatic pressure distribution. So you might have studied in fluid mechanics also. So it is a triangular pressure distribution. It increases with the depth. Why it is more at the bottom? Because more and more fluid layers rest above that particular point. So if you are considering this point, there are more fluid layers resting upon that particular point, and that is why it adds on to the weight, and thus the pressure is higher at the, as we go away from the free surface. So at this point your pressure is higher. Now the hydrostatic pressure is valid only in case of parallel flow, that is where the streamlines have neither substantial curvature nor divergence. Okay, so if you're, let us say, in case of a waterfall, if your streamlines are this way, sudden there is, so there at that particular point, your hydrostatic pressure is not pressure distribution is not applicable. So that brings us to our next discussion point. So the law of hydrostatic pressure distribution is applicable to which kinds of flow, whether it is applicable to uniform flow, gradually varied flow, or rapidly varied flow. So that is a point which we have to ponder upon, that what is the validity of this hydrostatic pressure distribution. Okay, now here we can see a small comparison between two kinds of channel. So channel slopes. So first you have a channel with a very small slope, and second you have a channel with a very large slope. So you can see this channel with a large slope. So the datum, let us say the datum is the same, but when you talk the pressure distribution channel with small slope, it is just simply gamma into h, where h is the total depth of water. At a particular instant, if you want to find the depth of water, based on that you can find the ordinate of that pressure. But when you have a very large slope, so in that case, since your depth that is resolved into two components or any force, let us say if we take a small control volume and there are forces acting on it, so it can be resolved into two components. So in the direction of gravity, because this is the direction of flow along the gravity, your cos theta component is predominant. So the pressure distribution will be gamma h into cos theta. So that is the difference which you have in large slope. So channels of large slopes are very rarely encountered in practice. Typically in spillway or chutes, they are there, that a spillway will have a very large slope. Also, in case of steep hills, there can be this large slope. Otherwise, it will be usually small slope. Now, most of the canals, rivers, and streams which we design, that commonly have very small slope. So your sine theta will be very small in that case. So corresponding to this, your sine theta is very small. So let us say if sine theta is very small, then your cos theta will be 1 for that cases, and thus we, because if sine theta is small, that angle will be closer to 0 degree. So if because sine 0 is 0, so then cos 0 becomes 1, and that is why for very small angles, this if you can use this equation only, you can take this theta as very close to 0, and then you get the cos theta is 1. So that is the difference between the pressure when you're taking a channel with a small slope as well as a large slope. Now that was about the parallel flows. What if your flows are not parallel? That is, the streamlines are curved. So in case if the curvature of streamlines is substantial, the flow, we define it as a curvilinear flow. Okay. So the effect of curvature would be to produce appreciable acceleration component or centrifugal forces that are normal to the direction of direction of flow. So their curvature will induce additional acceleration, and that can lead to increase in the acceleration component that is normal to the flow. Now, in that case, your pressure distribution will no longer be hydrostatic, and that depends on two cases, whether your curvature, that is convex or it is concave. So you can see there are three cases. So in this first case, you have a parallel flow. So your water is the pressure distribution is hydrostatic in this case. So it is a parallel flow. In the second case, you can see that it is a second and third are curvilinear cases. So it is a convex flow. So second one is a convex flow and third is a concave flow. So in case of convex flow, you can see that the pressure, now here you can see the piezometer is also attached. So piezometer shows a reading less than the actual water surface. Okay, so that means your pressure, that, so if we talk about the hydrostatic pressure condition, so your hydrostatic pressure, let us say it is WH. So your pressure in case of a convex flow, that will be a W or gamma, that is one and the same. It is gamma H minus gamma C. So there is a reduction in the pressure because of, due to this convex nature. In case of concave, this is a water surface, so your piezometer meter level is higher, that is by an amount C, that is the depth of piezometer above the water surface, and thus the pressure is additive, and thus your total pressure is gamma H plus gamma C. So in case of concave, the pressure is additive. Okay, so to summarize that, in case of concave flow, the centrifugal forces are pointing downwards to reinforce the gravity action. So what they do, they reinforce the gravity action, so they are along the gravity, and the resultant pressure is greater than the hydrostatic pressure. In convex flow, they are acting upward, that is against the gravity, and thus the resulting pressure is less than the hydrostatic pressure. So we have drawn the hydrostatic pressure, and this is the resultant pressure. So on similar lines, when there are divergence of streamlines which are appreciable enough, then the acceleration components will be very significant, and the hydrostatic pressure will also be disturbed accordingly. So that also has to be care whether your flow is diverging. That aspect will also come into picture to modify your pressure distribution. So this three figures are very well understood, that in case of parallel flow you have a triangular distribution. Convex flow, since the centrifugal force are pointing against the gravity, you have a lesser than the hydrostatic pressure distribution, and third case it is the opposite of that. Now moving to the governing equations of open channel flow. So there are three basic equations which govern the open channel flow. That is a continuity equation, that is the law of conservation of mass when we talk in solid mechanics, energy equation, that is law of conservation of energy, and the momentum equation, that is the impulse momentum relation in solid mechanics. So these three are the governing equations in your open channel flow. So coming to the continuity equation, so your continuity equation for steady flow, that is well known to you, that is q equal to a1 v1 a2 v2 a3 v3, and that is constant. So for steady flow it is very simple. Now coming to the unsteady part, so for the unsteady flow, so in case of unsteady flow, you know that the water will be added or subtracted, so due to that, there is unsteadiness of the flow. So you have a discharge q1, and there is another discharge q2, so that is happening, and the water surface elevation at any instant is given to you. So at next instant, what is the case, that your water surface, that at time t plus delta t, that is being observed, and that is observed between two sections which are placed at delta x apart. So this is the cross section where your t is your top width, y is the total depth of flow, this is the cross section area of the flow, this entire is a cross section area of flow, and we take a small elemental strip dy, and that is having area as dA. So your top width is given as t, that is equal to dA by dy. So that is the top width of the channel. So the net inflow into the element in time t can be written as the difference between q2 minus q1, that is the change of discharge with respect to your with respect to space. So it is del q by del x into delta x for this length delta x of the that is a longitudinal distance. Now what is the excess volume flow rate in time delta t? So this we multiply by the time, so this entire term, so del q by del x into delta x into delta t, so we are multiplying by time. So next, the storage volume at depth y. So what is the storage volume at depth y? That is A into delta x. So whatever area, that into length, so you will get the volume at a given depth. So that is A into delta y, delta x, that will be the storage volume at depth y. Then we'll find the rate of decrease of storage in time delta t. So that is, since it is a rate of decrease, we put a negative sign, so it is minus del by del t into the total volume. What is the volume that is being stored, how it is decreasing? So A into delta x. So we will just make it a derivative, so this will become del A by del t. Okay, so representing this as, this is del A by del t, and we are uh, involving the depth term also, so it is del A by del y into del y by del t. into minus delta x. So again, rearranging this term, we know that is the top width. So it becomes minus delta x t into del y by del t. So the decrease in storage in time delta t, that is minus t into delta x del y by del t into delta t. So by continuity equation, we'll just equate the total flow rate, that is the excess volume flow rate, to the decrease in storage. So that becomes del q by del x into delta x delta t, that is equal to minus t delta x upon into delta y del y by del t into delta t. So delta x will cancel out, delta t will cancel out, and whatever is left, that we rearrange and we get the equation, that is del q by del x plus, so this will come to this side, so plus t del y by del t, that is equal to 0, and this is the continuity equation for the unsteady flow. So you will have this continuity equation for the unsteady flow. Moving ahead, next is what the second equation which we discussed, that is the energy equation. So according to this energy equation, the total energy at a downstream section differs from that at the upstream section by an amount equal to the loss of energy between the sections. So this is similar to the Bernoulli's equation, which you studied in the pipe flow. So that is also an energy equation. It is a form of energy equation. So if you neglect the effect of curvature on the pressure distribution, the total energy head of the fluid at a given point A at a depth D below the water surface is. So you can see this figure. So in this figure, this is section 1, this is section 2. So you have the depth y1, here you have depth y2. Okay, now in the figure you may appear the curvature is excessive, but it will be a very, the length L is very large, so the curvature can be neglected in that case. So at this point A, which is at D depth below the free surface, so what will be the total energy? So that is H is the total energy, capital H, that is equal to ZA, that becomes your datum head, plus D cos theta, so that is this is the slope theta, so the cosine component in the direction of gravity, plus alpha V square by 2G. So the total energy at the section in general, if we write, becomes H is equal to Z plus Y cos theta, that is Y is the total depth of flow, plus alpha V square by 2G. If the channel slope is very small, then your cos theta becomes 1, and then your H is equal to Z plus Y plus alpha V square by 2G. So if we apply this energy equation at both the sections, then what you get, that Z1 plus Y1 plus V1 square by 2G, that is equal to Z2 plus Y2 plus V2 square by 2G plus HL. Now there can be a case where you can get different alpha 1 and alpha 2 also. Usually they may be same if there is not appreciable changes in the channel characteristics, but there may be case where your alpha 1 and alpha 2 can be different, and the third component, that is head loss, which occurs due to this. So that brings us to our next discussion point, that in this figure you saw there are three major slopes. So one is your bed slope, one is this your water surface slope, and third is your energy slope. So would the bottom profile, water surface and energy lines have the same or different slope at a given section? So at a given section, would all these three have same or different slope? That is what your question is. So just analyze the factors which affect these water surface energy line, and based on that comment on this answer. Okay, now moving to the last part, that is the momentum equation. So the linear momentum equation states that the algebraic sum of all the external forces that act in a given direction on a fluid mass equals the time rate of change of linear momentum of fluid mass in that direction. So for steady flow, the rate of change of momentum in a given direction will be equal to the net flux of momentum in that direction. So this is a control volume. So control volume is a region of the region defined space. So in this, there is a flow entering and leaving the control volume. So what are the forces? You have force F1, you have force F2 acting in the opposite direction. Then there is a F3 which offers resistance, and F4 is the body force. So these all forces have been indicated here. So we can apply have a sign convention, and then based on that, let us say the forces in the direction of flow can be taken as positive, other forces can be taken as negative. So by linear momentum equation, we have sigma f, that is summation of forces, that is F1 and plus F4, that is in the direction of flow, and F2 and F3 were in the opposite direction, they are taken negative. That is equal to m2 minus m1, where capital M is the momentum flux. So that is given as beta rho qv. So we already discussed when we are discussing the correction factor. So that is beta rho qv, that is a momentum flux. Okay. So the momentum equation is particularly useful in analyzing the rapidly varying flow condition where energy losses are complex and it cannot be estimated by applying your energy equation. So where energy equation is constrained to apply, there will apply this momentum equation in that situations. Now, if there is an unsteady flow, there is an additional term which adds, that is from the steady flow equation, you get one more term, that is a rate of change of momentum in the control volume. So that is an additional term which adds in the unsteady flow. So it states that the momentum equation for unsteady flow, that algebraic sum of all external forces in the given direction of a fluid mass equals the net change of linear momentum flux of the fluid mass in that direction plus the time rate of increase of momentum in that direction within the control volume. So the rate of change of momentum, that is a very essential component when you are dealing the unsteady flows. So with this we complete our second lecture, and hope you had a good learning. So just go through it and we can discuss the next point. And the next class we'll move ahead with the next topic. So thank you very much. Have a good day.